Okay, it's my pleasure to welcome everyone to the Infinite Games workshop. And today's speaker is Ilkka Törmä from the University of Turku in Finland. And he's going to be speaking about something I'm really excited to hear about, which is the complexity of the winning condition in infinite hex. And I'm very interested in this because when Davide and I wrote our paper on infinite hex before, this was an open question and we just didn't know what the complexity was. Sort of superficially, the complexity looked sigma 1,1, analytic, but we suspected it might be much, much simpler and perhaps even arithmetic. And I'm very glad to hear that that's the case, because this has important consequences for the determinacy of positions in infinite hex, which we now know will be determined. So without further ado, here is Ilkka speaking about the complexity of the winning condition in infinite hex.
Thank you, Joel, for the introduction. And everyone feel free to stop me at any time for questions or clarifications. So let me share my screen. There. All right. So the title is Infinite Hex is Arithmetic, which is sort of self-explanatory. As Joel mentioned, this is the main result of this presentation. So the paper or the manuscript is on archive, but it hasn't been reviewed or published yet. But this talk is based on this paper. All right, so hex is the finite version of infinite hex. It's a classical game. You have a board. It's shaped as a rhombus, and it consists of hexagonal tiles. Here's a 9 by 9 hex board. You can play it on different boards. I don't remember which size is the standard one. Maybe 11 by 11. Okay, but there are two players, red and blue. And on each turn, if it's red's turn, red chooses a tile which doesn't have a stone yet and puts a red stone. If it's blue's turn, blue places a blue stone. Okay, so the stones are never removed, and you cannot place a stone on a hex which already has a stone. So already you notice that the game will go on for a bounded number of turns. When the board is full, the game ends. Okay, and the goal of the red player, you notice that two of the sides are colored red and two of the sides are colored blue. The goal of red is to form a connected path from one side to the other, from one red side to the other red side. If red does so, red immediately wins. And the goal of blue is the same, except for the blue sides. Now it's a classical theorem that in any game of hex, there will be a winner and there will be exactly one winner. So if you have a full board, then exactly one player has won the game. And this has all sorts of nice connections to the Brouwer fixed point theorem and other areas of mathematics. Another thing which is sort of well known about classical hex is that the first player has a winning strategy. Okay, so because this is a finite game and there are no draws, then one of the players must have a winning strategy, and it turns out it's the first player because of a strategy stealing argument. So you you always sort of play a reflected version of the other player's strategy if you are the if the second player would have a winning strategy, then the first player would would pretend to be the second player and win, because having more stones is always an advantage. Then the infinite version of this is played, of course, on an infinite board. So you have an infinite hexagonal tiling of the two-dimensional plane r squared. So this was introduced by Joel and David last year, I think, 2022. So the rules for each turn are the same. If it's red's turn, red picks a vacant tile and puts a red stone. If it's blue's turn, blue picks a vacant tile and puts a blue stone. Now the question is, how should we define the winning condition? Because it's not obvious what happens on an infinite board. You have no borders on the infinite board. So what is the thing you should be trying to connect? And at what point should the game end? There are many possibilities that are explored in the paper of Joel and David. But this is the one that they deem the most natural, or the one that best corresponds to the winning condition of finite hex. So a position of infinite hex is winning for red if on the board there is a two-way infinite path of adjacent red stones, which are at some positions, xi, yi, such that for each position xy, we have eventually in the positive direction, xi is greater than x and yi is greater than y, and in the negative direction, x minus I is less than x and y minus I is less than y. Okay, so what this means, you have a if you have a northeast half plane, which is everything that is in the positive quadrant translated by xy, when you go in the positive direction of this path, all of the red stones eventually must be in this quadrant. And the same for the negative direction and southwest half planes. Okay, so if I draw a picture, I have here my my red path. The red path goes somewhere like this. And I require that on every quarter plane like this, the path eventually will lie in here. And on every quarter plane like this, eventually, from some point on, maybe from here on, the path stays inside this quadrant. Okay. So you can say that the path connects minus infinity to plus infinity in the limit. The winning condition of blue is the same, but you rotate by 90 degrees. So you use the northwest and the southeast half planes. And because this winning condition cannot be true if there are only finitely many stones on the board, it takes at least omega moves to reach a winning position. So you have to play for an infinite number of turns. And then when you have played for an infinite number of turns, you look at the board and see if either player is the winner. Now the theorem, one of the first theorems in this paper is that a position can be winning for at most one player. It cannot be the case that both red and blue are winners, because then you would have the red and blue paths would have to cross each other, which is of course impossible. The main theorem of the paper, or at least what I interpret as the main theorem, is that with perfect play, infinite hex is a draw from the empty starting position. Okay, so Joel mentioned this briefly in his talk. So there is a sort of a mirroring strategy in which the second player can block the first player from winning. And then, of course, the second player cannot have a winning strategy for the same reason as with finite hex. Okay, so from the empty board, both players can force a draw. But the question is, does the same hold from every starting position? So when you start the game, suppose you have put some number of stones on the board. And then the players from this position, from this position, they start playing the game. Is it still the case that the game is a draw, or does either player have a winning strategy, or maybe is the game undetermined? That there are no winning or drawing strategies for either player. With the axiom of choice, you can construct these sorts of paradoxical games. And the question is infinite hex one of these games? So even for a board with some, let's say four initial stones in some positions, it's not clear which player has a winning strategy, if any. Okay. Now the main tool for proving that some game is determined, so every player has so every position either admits a winning strategy or a drawing strategy, is the Borel determinacy theorem. Okay, suppose we model the infinite hex as the game as a game of on omega to the omega, so the game of a game of sequences of natural numbers. So at position I, you put the index of the hex where the ith move places a stone. And then you have an infinite sequence of numbers. And from this sequence of numbers, you can reconstruct the game and see who is the winner. And if the set of winning conditions, say for the first player or the second player, if they are Borel sets, then this theorem of Martin, the Borel determinacy theorem, says that every position is determined. So either there is a winning strategy for one of the players, or there are drawing strategies. So a problem that would imply a solution to the other problem is the winning condition of infinite hex a Borel set. If it is, then it is a determined game, and so it's well behaved from a game theory perspective. Okay. And my result is that yes, it's in fact a Borel set. And so here I note that what I call the winning condition is a subset of positions, which is a slightly different thing than as we model it by these sequence games. But still, if these sets of winning positions form an arithmetic set, then the winning set of this sequence game is also an arithmetic set. Not necessarily of exactly the same complexity, but you do get the determinacy result.
Could you explain that a little more? This distinction you're making?
Yes. So here, what I call the winning condition is a set of positions. So sets of placements of stones on the hexagonal board. And you can see it as a coloring of z squared if you want to. So this is some set of colorings, and I'm looking at the subset of those for that are winning for red, that contain this sort of an infinite path. And in this model, we are looking at the entire history of the game, sort of at what point did I put the stone in this position. So this, like as as subsets of some topological space, these are a bit different, but there is a nice enough correspondence so that if these winning sets if these winning positions form a Borel set, then so do this. So you maybe have one exists quantifier more, so that saying that, okay, instead of saying that there is a stone in this tile, you say that there exists a time so that at this time a stone was placed in this position. This is actually something that I didn't fully realize when I was writing the paper. I only realized it now when I was writing these slides. All right. Anyway, so the winning condition of infinite hex, taken as a subset of colorings on which there is such an infinite red path. This is a delta 0,5 set. In particular, it is a Borel set. I also have a lower bound for the complexity. This set is sigma 0,4 hard. So there is still a small gap between these, which I do not dare conjecture which way it goes, if any, or what is the actual position of this set in the Borel hierarchy. All right. So for the rest of the talk, I will at least sketch the proofs of both of these bounds. All right, for the upper bound, the delta 0,5 bound, I will find a formula that describes this condition of having the infinite red path. It will be a Boolean combination of sigma 0,4 and pi 0,4 formulas, so it will define a delta 0,5 set. And now for this, I will first have some auxiliary definitions. So I fix some sequences of northeast and southwest quarter planes. So q plus n and q minus n. So let's say that this will be rather this can be rather arbitrary, but I'm using my stylus the wrong way. Let's say that here is q plus 1, then inside it is q plus 2, then inside it is q plus 3, and so on. This is just some nested sequence of of these quarter planes. And then here I have q minus 1, here I have q minus 2, and so on. Another thing I will discuss or use in the proof is when you have an edge which is between a non-red tile and a red tile. So it is a border of some connected component of red tiles. Then we see the entire border of this component as a sequence of such edges. So here, if I have let's say I have a hex here which contains a red stone, and I'm looking at this edge here. So if let's say that on this hex I have a red tile and here I do not, then the next edge on the sequence is this one, and then the next is this one. If I have a red stone here, the next one is this one, and so on. So this is basically just an enumeration of the border of a connected component of red tiles taken in some consistent direction. Let's say that I keep the red stones on my right hand side. So these sequences are usually used in the classical proof that the game of finite hex has exactly one winner. So you analyze how the borders between the
Question.
components go. Yes.
I have a question. So supposing that picture you just drew, that the top hex does have a red stone, but it's the fourth stone on the Z chain, then what happens to this edge? Because you would seem, if you wanted to keep the red stone still on the right, it's like you'd have to turn around and reuse the same edge again, or what would you do in that case?
So here?
No, the one that you had is empty, that one.
Here. Okay, then
but maybe you went from left, bottom, right, and then that one.
In this case, I would have turned here.
Okay, so you're not going to use the entire Z chain if you have that sort of extra stuff on it.
Yes, so I'm basically, if this only makes sense if on this stone I don't have a red. In here I don't have a red stone.
Okay.
In this case, I can start such a chain of edges. If I already have a red stone here, then it doesn't make sense to talk about the chain of this edge. Does this make sense now? All right. So there will be 3 auxiliary formulas. The first one is this. There exists a red tile T, which I call the anchor, such that for all n, there are tiles A in Q plus n and B in Q minus n, which are connected to T by some path of red tiles, such that A is connected to infinitely many red tiles within this quadrant that it lies in, and similarly for B and the other one. So this is a sequence 4 formula that exists for all, exists, and for all. The last one is that for all K is the set of tiles that are connected to A within this component as list size K. So this can be done with the for all quantifier. So in words, there is a single tile T, which for every n is connected to some infinite red component of this Q plus n and Q minus n. Okay, so there is a single red tile T, so that's whenever you take whichever quarter planes you choose, you can find an A here and a B here, which are connected to T like this, so that A is connected to an infinite number of red tiles here, and B is also connected to an infinite number of red tiles here. Okay. Note that these sets, they don't have to go near minus infinity or plus infinity. They just have to be infinite, so they can stay close to the border of this quarter plane if they want to. Okay, so this is phi 1. Now phi 1 by itself doesn't guarantee a red wheel. Even if we require the stronger property that A is connected to every sub-quadrant within Q plus n. And this kind of coloring is a counterexample. So we have an infinite line coming from minus infinity to minus infinity, and then an infinitely branching vertical line, and each branch makes its sort of increasing detours to the north and then back to the same horizontal line. Okay, this is not a winning position for red because you cannot find a single path that would go to plus infinity, but it satisfies this even stronger variant of phi 1. Basically because within every Qn, you choose a path which is eventually in Qn, and then because it goes up arbitrarily far, you can get to every Qn. Okay, so we need that further conditions to our formula. This is the formula phi2. It is a π04 formula. It says that for all n, there exists an R such that for all edges beta between red and non-red tiles, which I talked about earlier, on the border of this quadrant, which are at distance more than R from the corner, so basically for all but finitely many of such edges, this sequence of edges given by beta leaves this quadrant when you traverse it in both directions. Okay, so what does this say? You say that if we are looking at the plus version of this, it says that for all quadrants at some finite distance from the corner, if you see an edge between a red and a non-red tile, then, okay, if you go in this direction, you will, of course, leave this quadrant immediately. But in the other direction, you also have to leave the quadrant. Okay. So equivalently, you can say that all but finitely many of the red components that intersect the border of this quadroplane are finite. So here you can have some infinite red components that intersect the border of this quadrant. But outside of this region, all of them have to be finite, because the path that defines the border of this component eventually has to come back and close off this finite component. Equivalently, each Q star n has a finite number of infinite red components that intersect its border. Does this formula make sense to you? More or less. And the last formula is phi3, which is again a sigma 4 formula. And it says the following. There exists an edge beta between a red and a non-red tile, such that for all n, there is an I0 and a sign S, so that for all large enough I, we have beta Si is in this quadrant. Okay, so this says that there is a component, a connected component of red tiles whose border, if you traverse it in either direction, it will eventually lie in every quadroplane Qn. Okay, so the S tells you in which direction you traverse the border, and this says that for all I bigger than this bound, it is in this Qn, and this should hold for all n. Okay. And the idea of phi3 is that if this is true, then you have like you don't just have a red path that goes to plus infinity. You can actually find one that is that is on the border of a red component. So you can follow a border of a red component and go to plus infinity.
Could you explain what the subscript means on beta? If beta is just one edge, or is it the whole sequence of edges? Or
so if beta is the edge, then beta k is the sequence of edges that it defines.
Okay, that continues either in the one direction or the other along the boundary of that component.
Yes.
Okay.
Yes. So in pictures, you can say that there is a boundary between a red hex and a non-red hex, so that if you in at least one direction follow this edge, you will eventually you will eventually be in every quarter plane like this. All right. And then I claim that this formula, phi, is equivalent to a red win. So I'm saying that, okay, phi1 must hold. So I must have this anchor tile that connects to infinite components in both directions. Then in the plus direction, I have either phi2 or phi3. And in the minus direction, I have either phi2 or phi3. So these are, one of these holds in either direction. Okay, so in the plus direction, either I always have a finite number of these red components, or I have an edge that goes to plus infinity, and the same for the other direction. Okay. And because this is a Boolean combination of these sigma 04 and pi 04 formulas, it defines a delta 5 set of positions. Okay, and now how I prove this is I have two sort of geometric lemmas. So lemma A says that if phi1 holds and each of these quarter planes has only finitely many infinite red components which are connected to the anchor tile, then red wins. So there is a winning path for red.
When you refer to the infinite component here, do you just mean the part of it that's in Qn, or do you mean it as a component in the plane?
Just the part that is in Qn.
Okay, and that's what phi2 is talking about, right? There.
Yes.
So it says if I say all the components that touch the border outside of the distance R are all finite in Qn, but they might actually all be connected to each other, right?
Yes. Yes.
Okay.
So they might be infinite on this side, and they might be connected to these infinite components, but we are only interested in what happens in Qn.
Okay, thank you.
Yes. Okay, and this lemma is proved using Koenig's lemma. So basically, you can define a tree, an infinite tree, whose vertices are these infinite red components of these different Qn's. And because there are only finitely many on each quarter plane, the tree is finitely branching, and then you can find using Koenig's lemma an infinite path in this tree, and then from the infinite path in this tree, you can extract an infinite red path close to plus infinity. So there are some technical details. In particular, Q1 guarantees that this tree is infinite. But this is the basic idea of this lemma. Okay, and lemma B says that in the other case, if some, let's say Q plus n, has infinitely many red components that intersect its vertical border, and of course the analogous thing holds for the horizontal border. But if we have infinitely many components that intersect the vertical border, then the edge sequences of those components will visit a vertical line only finitely many times. Okay, this is sort of a technical condition. But basically the idea is this: you have this quarter plane, and let's say that okay, there are some number of infinite red components here, infinitely many of them. And now I say that this path of the red edges, it cannot intersect any vertical line an infinite number of times. Okay, why is this? Okay, suppose that it does. Infinitely often it returns to this vertical line there. Every time it does, it creates a gap between this line and the border of this quadrant. And all of the other components that we have created between here and here, they have to be able to squeeze between these two lines. Okay. And once we have more components than we have tiles on this gap, we run into a contradiction. Okay. So if you have an infinite number of components, then the edge sequences are forced to like tend to the right eventually. Now they might all be horizontal for all we know, but they cannot go upwards, so to speak. They have to tend to the right. Okay, so this is lemma B, which is used several times in the proof. Okay, phi implies red win. This is a proof by contradiction. So we assume that phi holds, but red does not win, and say it does not win toward infinity, infinity. Okay, so there is no red path to plus infinity from this anchor tile. Okay, then by lemma A, we know that some q plus n has an infinite number of infinite red components, which are connected to the anchor tile. Because otherwise, by Koenig's lemma, we can extract an infinite path. In particular, phi 2 plus does not hold, because phi 2 says that there is a finite number of such components. So phi 3 holds. There is somewhere an edge sequence that goes to plus infinity, plus infinity. And now you can argue that this forces the border of some of the infinite components to also go to plus infinity. Because this phi 3 is sort of below one of these components. If there is an infinite number of components on the vertical line, say. So it forces we know that the edge sequence of that component, it cannot go directly up, and because this edge sequence is below it, it also cannot go horizontally. And so we see that actually red wins, and this is a contradiction, because we assume that red does not win. The other direction, a red win implies phi. So first of all, a red win implies phi 1. So there is an anchor which is connected to infinite components. Just choose all of the tiles from the winning path. Okay. Then let's assume that that phi 1 plus does not hold. So it means that some qn plus has an infinite number of red components that will intersect the border. And now, in the previous proof, we had the edge sequence given by phi 3. Here we have the winning path, which we assume that exists. And in the same way, it forces the border of some red component to go to plus infinity. And this border is a witness to phi 3 plus. Okay, so if we know that phi 1 wins, and if phi 2 does not hold, then phi 3 holds. So phi 2 or phi 3 holds. And the same for in the negative direction. Okay, so this concludes one of the directions, or one of the bounds. So the winning set of red forms a delta 5 set. In particular, it is a Borel set, so the infinite x is determined. And there we start in position. Now, I also have the lower bound of being sigma 0 for hard. So for this, I will make some auxiliary like technical definitions. So we let P be the set of all positions. So I index all the hexes by omega, and then this is just vacant and red and blue. So this is a coloring of all the hexagonal tiles by vacant and red and blue. And let W be the subset of those which are winning for red. And sigma 04 hardness means that for all sets which are sigma 04, so all sets of this form, intersection, union, intersection of these basic global sets. For all such sets, there is a continuous function from here to P, such that the X is exactly the set that is mapped to the winning positions. Okay, here I should also have 0, 1. 0, 1 to the omega, but okay, doesn't matter. Okay, so I'll take a set X of this kind. So it basically says that X is defined by a exist for all condition. And I must find a continuous function which maps X to W. Okay, as a first step, I reduced the case where X has this form. So exists A for all B for all but finitely many C. This condition holds. So there is a standard reduction for doing this. So I like to think these things computationally. So what you do is you start enumerating for every C. You are looking for a C for which every D is good. So you start from C is 0, and then you start enumerating Ds. Once you find a bad D, you jump to the next C. When you find a bad D for this C, you jump to the next C, and so on. And this condition says that eventually I will not find any more bad Ds for some C. So I can transform my set this definition into one like this. Okay, so X is A for all B for all but finitely many C. Okay, and then I will define the function f. So f of x is a position of the game, and it has the following structure. It has an infinite diagonal path coming from minus infinity. At the origin, it turns north and branches to infinite many paths pi. Similarly to the example that shows that phi 1 doesn't guarantee a red win. Now for each path pi, there is a sequence of tiles that it always visits, independently of what x is. And this sequence of tiles, it tends to infinity, but it has gaps. And in the gap between Tij and Tij plus 1, this path will dip down to some horizontal line. And which line it dips to is determined by this element x. Okay, so here is a diagram of the structure of a position. You have an infinite path coming from here. Then it branches into infinitely many of these paths pi. So here is one of the special tiles. Here is the next one. Here's the next one. Here's the next one. So the sequence of special tiles goes to the right and to the north. And in between, this path will dip down to some of these horizontal lines. And you can see that the next one cannot dip lower than the path that is below it.
So the dipping down is finding a bad D, is that correct?
Yes, it more or less corresponds to finding a bad D.
Okay.
Yes, and now some of these paths can decide, okay, I'm not going to dip down as far as I can. I'm only going to dip down here because of because of some condition in X.
But maybe you could label, like C is the distance you are out in this picture, and B is the height of the branching or something like that. Is that right?
Yes. So the
is it possible to label with the letters?
So the branches will correspond to different A's. So this is A equals 1, A equals 2, A equals 3. So each A has its own path.
Okay.
And here, so there is not an exact one-to-one correspondence between these vertical lines and these numbers, B, C, or D. Basically, okay. So let me show the next slide. So maybe it's clearer. Okay. So on step J, so J is one of the horizontal lines. On step J, if there is a B, which is at most J, so that X does not belong to this set. So this is a bad B. Then the path tries to dip to line I plus B. So KI is the lowest line that PI will ever try to visit. And so it dips B lines to the north of it if it finds a bad B.
Yeah.
Okay. Now the lower paths have priority.
Any fence to the right of I.
Sorry. Can you repeat? Okay. I didn't hear the question. If there was a question. Okay. So the lower paths have priority. So if PI tries to dip down, but PI minus 1 is in the way, then PI only dips as far as it can, and then later, as soon as it can, we'll try to dip even lower, up to the line it has to dip to. Okay. And now red wins. I claim that red wins if and only if some path will not try to dip to any single line infinitely often. Okay. If there is a path that will try to dip to some line infinitely often, okay, so yes, so if some path will only try to dip to any line only finitely often, then it will not it will actually not go to any line infinitely often because it will not even try to dip there. And if all lines will try to dip to some line infinitely often, then you can prove by induction on I that path PI will actually dip to some line infinitely often. So this is true for the lowest line, of course, because it has no obstructions. And then the next one is obstructed by the lowest line, but the lowest line does visit some line infinitely often, so the next one will also, and so on. Okay. And this is equivalent to X being in X, so in this set. So for some A, for all B, eventually it is in C. Okay, and why is this? So we look at the path PI, which does not try to dip to any single line infinitely often. Then it means that for any B, eventually for all large enough J, it will be here because we do not dip to this line. We do not try to dip to this line Ki plus B anymore. And so it will be, X will be in this set for all large enough J. And this shows that the small x is in this set. And conversely, if all paths pi try to dip to some line b infinitely many times, then it means that for infinitely many j, x is not in xibj, and so x is not in this set x. Okay, so third winning is indeed equivalent to x being in this set with x. So we have a correct reduction. And in fact, this reduction works both in the boldface and the lightface hierarchy. So if x is given by a computable sequence of sets, then we can have a computable function f that realizes this. All right. So there are some open problems still. First one is the gap that I have between delta 0,5 and sigma 0,4. So the formula phi, it contains this by pi 0,4 subformula. So it's not sigma 0,4. And I keep having lots of trouble trying to modify it into a sigma 0,4 formula. But on the other hand, I have not been able to prove pi 0,4 hardness. It's not clear how the first for all quantifier should be used. So I don't know what is the exact position. Is it sigma 0,4 or is it delta 0,5 properly? Another thing that interests me is if we play infinite hex on some other tiling than this tiling by regular hexagons, how does this affect the complexity of this set W? So you can have like any tiling by finite polygons, and for example, this lemma B is no longer true if, let's say, that the tiles get smaller the further away you go from the origin, because this lemma B, as I proved it, is based on the fact that if you have a gap of some length, there is a bounded number of sets that can squeeze between the gap. But if the tiles get smaller and smaller, a gap of the same length can have more and more sets going through it, and so lemma B is no longer true. And conversely, suppose that the tiles get larger and larger the further away you go from the origin. You cannot form this kind of a configuration anymore because you don't have enough room on the right for the different paths to dip to these lines. So the geometry of the tiling probably has some effect on the complexity of this set. I don't know what exactly, but it would be nice to determine. All right, I think I'll stop here and we can start the discussion.
Well, thank you very much. So let me change to the gallery. Right. Does anyone have any questions? So Jack, I'm sorry, I may have accidentally muted you because I wasn't sure if you were trying to ask a question or not, but maybe if you didn't have a question, then go ahead. So are there any questions?
If Jack does not have a question, I would like first of all to thank Ilkka, and thanks for the talk and also for bringing some clarity. That was very appreciated. And I want to ask you about this second open question. So do all your results hold in the case that you kind of fix a minimum and a maximum size of all the tiles in the plane?
I suppose they do. So if you have, let's say that every tile is contained in a ball of radius big R and contains a ball of radius small r inside it and is a polygon, then all of this should hold. So the complexity should be the same as for the regular hexagonal tiling. Of course you have to take care of how you handle these sequences of edges and how you define the adjacencies, because for example here, let's say you instead of the hexagonal tiles you have the square tiles. Okay, you have a red tile here, you have a red tile here, here you don't have a red tile, here you don't have a red tile, and so you should define that these two red tiles are not adjacent in order to prevent from like a non-planarity. You still want to prevent the both players winning at the same time, right? This is sort of essential to keep this condition. And so if your edge sequence comes from here, then it should turn down here. And if your edge comes from here, then it should turn up here. So there are some small subtleties on how to handle this, but as long as you make sure that you don't create anything non-planar, then everything should work out nicely.
Yes, with the square tiling, if you just shifted the rows like a brick pattern, then this issue wouldn't arise about, crossing in the corners, right?
Yes, but
so
then it's equivalent to the hexagonal tile.
Yeah, I think so. Yeah. So I have a question actually about that. So I guess from these remarks at the end about sort of alternative tilings, you're imagining different versions of infinite hex that are played, on different kinds of boards instead of the usual hex tile. And are you imagining something like a, hyperbolic kind of board hex thing, or, where the curvature is different so that the hexes get tinier and tinier as you go out, but locally it looks like a hex board? Is that the kind of thing you're imagining, like playing hex in hyperbolic space or something,
that's one thing we can imagine. So we can take the hyperbolic space and project it somehow.
Right. It would break your proof, right? Because in hyperbolic space, you can fit a lot in this tiny gap, right? I mean, because it's not actually so tiny anymore. I mean, in that space. So that's quite interesting, I think. I wonder though if it's fruitful to think graph theoretically instead of having a board tiling, really hex is played on a graph. You have this connectivity. And maybe you could formulate the winning condition, graph theoretically, so that tiles are adjacent, when they count, as if you have both of those, then that counts as a winning connection, right?
Yes, but somehow you still have to, you still need to have a direction. You want to have, if you have an infinite graph, you want to have a condition that talks about paths going from minus infinity to plus infinity. So from one direction in the graph to another direction in the graph.
So they should be planar, but then it depends on how you put them in the plane or something. Yeah, I'm not quite sure what the right way to do it would be.
Yes, so perhaps you could play on a planar embedding of a graph.
Right.
Or maybe more abstractly. So you could just abstractly define these q plus n and q minus n subsets of the graph.
That's true.
So some nested sequence of subsets.
Right.
And then you require that the path is eventually in q plus n in one direction and q minus n in the other direction.
Right. Oh, that's a nice way to think about it. So for any graph, even like a uncountable one or something, you could maybe have these sort of these cones going to the edges that define the corners that you're trying to win and get into, right? So, but I guess if you still want a Z chain, then maybe, I mean, it could be uncountably branching or something. Why not? Yeah, I'm not quite sure. That's very interesting perspective about generalizing. Okay, are there any other questions? I wanted to say I was really pleased to see that you were using Koenig's lemma, because this is something that Davide and I had tried to do. I remember in my office in Oxford, we were at the board and I kept saying, oh, it's got to be compactness somehow. We have to get a finitely branching tree in there somehow. We couldn't ever make it work, but I really tried hard to make that Koenig's lemma argument work. And so I'm really happy to see that you were able to succeed with that plan. So fantastic. Yeah, really nice result. Okay, any other questions? So let's thank our speaker again then. And the next meeting is in 2 weeks, I believe. And I believe it's Andreas Zivas is going to talk about the finite position with gain value omega squared plus k. And so that will be exciting to see in 2 weeks. So I hope to see you all back here. And thanks for coming. Bye.
Thank you very much. Bye-bye.
Yeah.
Thank you.